Hi, this is Sanjeev and welcome back to my YouTube channel, Fun with Sanjeev. As I promised, I'm here with some tutorials on the basics of sound, or we could say the fundamentals of sound, aiming for those who want to become sound engineers in the future. So now let's understand what sound is. Sound is a kind of energy that is produced when you set an object to vibration. By itself, an object does not create any sound. The moment you hit it or strike it or pluck or do something with it, it creates sound. For example, you have a guitar, and when you pluck the string of the guitar, the string starts to vibrate, thereby creating sound. You have a snare, you hit the snare, and the skin of the snare starts to vibrate, and thereby creating a sound. Okay? So what really happens when this object is set to vibration? When the object vibrates in to and fro motion, the air particles surrounding the object also is set to vibration, thereby hitting more and more particles beside them and transferring that energy from one particle to another particle, and it goes on till it runs out of energy. Okay? So this is represented by this diagram over here, wherein you have this movement. It is pushing and then comes back mean position, goes to the other side, mean position, pushes forward, mean position, back side, mean position, pushes forward. Every time you push forward, you are seeing that the energy is being transferred from one particle to another particle, and this string of energy is going farther and farther away. Also, like, when you drop a stone in the water, it creates a ripple, right? So one ripple is created and that starts to go away from the source, and more ripples start to follow that. So that's not an example of sound, but we could think about how the waves go farther away from the source. So this movement you're seeing over here, this red particle is the air particle. So how is the movement of the air particle you're seeing here? It is going this way and backward, and this way and backward. So the movement of the air particle is parallel to the movement or the direction of the sound wave. So this kind of wave is known as longitudinal waves. Unlike the light waves, which actually movement is upward and downward, which is perpendicular to the direction of the light. Here it is in the direction of the sound waves. So we call that as a longitudinal waves. So we know that we are able to hear the sound because we are inside. We are in an atmosphere where we have the air. So air is one such medium that actually lets the sound go from one point to another point. So let's talk about the mediums in which the sound can travel. The sound can travel in three mediums: the gas, which is over here, the liquids, and the solids. All right. What we are seeing here is the gas molecules are pretty loosely packed. They don't have much great bonding. So what's happening is when the sound energy is in the air molecules, the transmission or the transfer of energy from one molecule to the other molecule is not so efficient because of this, the air gaps. The molecules are very loosely packed, but then still it propagates from one point to another point. The point is here, because since the energy transfer is not so efficient, the speed of the sound in air and the distance in which it propagates is comparatively limited compared to what? Compared to the liquids and the solids. So look over here, the liquids are much more densely packed compared to the air. the gas molecules, and therefore the energy transfer is going to be much efficient, and so we could say that the sound travels much faster and much farther in the liquids compared to the gas. What about the solids? Now you have the solids over here. The solids are very tightly packed. The molecules are very tightly packed, and so the transfer of energy from one molecule to another molecule is pretty efficient. They are instant, and so the speed of the sound in the solids are far more, and the distance it travels is also far more compared to the liquids and the gas. Okay, for one example I would give is that when you are standing next to a railway track, and you know that there is a train is supposed to be coming at this particular time. You know that train is going to pass through this track in a particular time. At that moment, when you stand near the track, visually or with your ears, you're not able to hear the train or see the train coming at a distance. But the moment you put your ears on the railway track, and if there is a train coming at a very long distance, you are able to listen to the sound of the train coming when you place the ears on the track, because the wheels of the train is rubbing against the tracks, and that vibration that is happening in the track travels that long distance so quickly that you're able to hear the sound. You remove the ears from the track and you try to listen it through the air. You're not able to listen to it because the energy is lost much far away. So if you look into this, the speed of sound in air is approximately 1235 feet per second or 343 meters per second. Liquid, you see that it is 4,862 feet per second, or it's around 1,482 meters per second. And look at solids, it's 19,553 feet per second, or it is 5,960 meters per second. It's pretty fast in the case of solids compared to the liquids and the gas. Now the point is, we have these three mediums. Now the next thing is, does sound travel in vacuum when there is no medium? Sound do not travel through the vacuum. Why? Because there is no medium. There are no molecules to carry this energy. So like illustrated here, we have this earth over here, and surrounding the earth we have the atmosphere. And slowly you're going farther from the earth, the density of the air molecules reduces and reduces and reduces. And finally, at one point, you have no air molecules, no atmosphere. So, whatever happens in this area of atmosphere, we are able to listen to. But those huge explosions and deafening sounds happening in the sun are not heard anywhere beyond this, so that you don't hear that kind of explosions happening down in the earth, because there is a section over here, the space, that's a vacuum. Okay, now we go to the next topic. We'll talk about the wavelength and the frequency. So wavelength, as you know, that it is the length of the wave. So what's a wave? Wave is a complete cycle. So if you look into this diagram, so you have a wave starting from this, and it goes up to the crest, it goes to the mean position, goes to the trough, which is the least air pressure, and comes back to the mean position. This complete cycle is one single wave. The length of the wave is obviously the wavelength. So to make it simple, to understand more clearly, we could also say the distance between crest and the next crest, or the distance between trough and the next rough is the wavelength. All right. So wavelength is the velocity of sound divided by its frequency. So wavelength is denoted by something called a lambda. So lambda equals c by f. So velocity of sound could be in meters per second, as I told you earlier, or it could be in feet per second. That depends on what kind of calculation or measurement you want to have the wavelength in. You want the wavelength in meters, you go for sound velocity in meters per second. If you want it in feet, you go for feet per second as sound velocity. So you also see that wavelength, which is lambda, which is inversely proportional to the frequency, which means that a high frequency has a tiny wavelength, and a low frequency has a large wavelength. So wavelength and frequencies are inversely proportional. Now we'll come to something called frequency. So we talked about a complete cycle. So this is a complete cycle over here. From here till this, and this goes to a complete cycle. Frequency is how many such cycles are happening in 1 second. Frequency F tells you how many such complete cycles are happening in 1 second. So 1 second is a time, and the repetitions, how frequent these number of cycles are happening, is the frequency. How many such cycles are happening in 1 second is known as a frequency. So in this example over here, you have 1, 2, 3, and 4. So you have 4 cycles happening in 1 second. So we call that as 4 hertz. Hertz is a unit of frequency. And if you look over here, you have so many such cycles repeating in 1 second. So we have 14 such cycles happening in 1 second, and so we call that as 14 hertz. So you look into this, in 1 second you have more number of complete waves clustered. It's more jammed compared to the 4 hertz over here. All right. So this is 4 hertz and this is 14 hertz, and our ears is able to identify or listen to frequencies between 20 hertz and 20 kilohertz, that is 20,000 hertz, theoretically. But I'll come to how our ear responds to the frequencies in reality a little later. All right. So we go to the next. So there's something else which is so similar to frequency, that is the pitch. So you got, he's got a high pitched voice, he has got a low pitched voice, high pitch, low pitch. We have heard that many times, right? A lot of musicians say that. But you don't say he's got a high frequency voice, he's got a low frequency voice. That's not said. So when you talk about musical terms, a frequency in musical term, we call that as pitch. He has got a high pitched voice. That's a better way to say that he's got a high frequency voice. What high frequency voice? Doesn't make any sense. So pitch and frequencies are quite related. They are directly proportional. High pitch, high frequency; low pitch, low frequency. But they are different. Why is it different? I'll tell you. You talk to a musician and say that, oh, play a frequency 440 on your keyboard. He would say, hey, what? I don't understand what you're talking about. Talk in some term that I can understand. The language you're saying, a frequency, is not a musical term. So you might say that, yeah, there is something called 440 hertz, but what is it represented as on a keyboard or in music? So that is known as a pitch A. So looking over here, you have 440 hertz over here. It's known as pitch A. So talk to a musician and say, play a pitch A, he would definitely play a pitch A, but he won't know what 440 hertz is. But A on a piano is 440 hertz, which means a pitch has a number, a frequency number. So you have a frequency number which is 440 hertz, which is called A. You also have an A over here. You also have an A over here. But all the three are A, but having different frequencies. One is 220 hertz, one is 440 hertz, another is 880 hertz. So you just see there is some kind of relationship between this A, and this A. This relationship is called the octave relationship. So A is 1, but we have 3 different frequencies, or maybe 4 different frequencies, or maybe 5 different frequencies to tell that they are in octaves. So when you have a middle A of a piano saying it is 440 hertz, a pitch an octave lower than the 440 hertz is half the octave, half the frequency, which means it is 220 hertz. And the frequency which doubles from the middle A of a piano is 880 hertz, still known as A. So we see that it's a halving of the frequency or doubling of the frequency, that is the octave. So this is the relationship between pitch and frequency. All right? Okay. So other than the frequencies that our humans can hear, which is, we call that as the human range of hearing frequencies, there are frequencies happening, lots and lots of frequencies happening other than this 20 hertz, 20 kilohertz in this universe. We may not be able to hear it, but it is there. A lot of frequencies are there. Those frequencies that fall below the range of our listening, which is 20 hertz, is known as the infrasound. And those frequencies that you are not able to listen beyond our range of listening, that is 20 kilohertz, are known as the ultrasound. So infrasound and ultrasound have got different uses. For us also, we may not be able to hear, but then we use them in different ways. Even some animals use them in different ways to probably communicate between the herds. Like elephants, giraffes, whales, they use a very low frequency tones to communicate at large distances, kilometers and kilometers, and say that, look, oh, I'm here. Okay, so that communication happens with infrasound for lots of animals. But what about humans? We use them to, for understanding or calculating or detecting volcano eruptions or earthquakes or maybe tsunamis. So we use microphones to detect these vibrations and understand whether there is we could predict a volcano to be happening in some time, or maybe an earthquake to be happening in some time, or maybe a arriving tsunami can also be detected using these detectors, low frequency or infrasound detectors. And what about ultrasound? Ultrasound is our frequencies, as I told you, which is beyond 20 kilohertz. So that can be heard not by human beings, but by a lot of animals like cats, dogs, bats. And you must have heard of something called dog whistle, right? So when you whistle that particular thing, we are not able to hear the ultrasound, but the dogs are able to hear. So the dog whistles are one example of an ultrasound. Bats use ultrasound to detect obstacles or maybe its prey. So And also, ultrasound is used in scanning your an unborn baby to check whether it is healthy, the position, and all those things. So these are the uses of ultrasound and also the infrasound. Intensity, amplitude. The amount of energy that is transported past a given area in a medium. So you have an area, an amount of energy that is being carried forward in that area in a given time is known as the intensity of a sound wave. Whereas an amplitude is a displacement between from the mean position 0, where there's no displacement happening, to a higher displacement. That's known as the amplitude. So amplitude over here, the red one over here, is say 20 decibels. And here you have say 60 decibels. And here you have 100 decibels. Decibels is the unit of the amplitude. So definitely intensity and amplitude are related. So more the amplitude, more the intensity. Lesser the amplitude, lesser the intensity. And they measured in decibels, dB. You must have seen in amplifiers, sometimes you have this volume knob representing certain decibels. You have -10, -20, 0, +1, +2, +3 decibels. So this tells you how loud you want that amplification to be. So we'll talk about what loudness is in the next chapter. But intensity is related to, or amplitude is related to loudness. More the amplitude, more the loudness. But still, there is a very important difference between the loudness and the amplitude. So here we end the class. Next chapter, we'll talk about loudness and we carry to more topics. So I would say thanks for watching. I hope you have understood this particular chapter. If you have any doubts, please don't hesitate to comment over there below and like the video and share it. And obviously, I should be telling you again and again, please subscribe and ring the bell icon so that the next chapters or any other videos that I'm going to upload, you will get an information or a message. Thanks for watching. Have a great day. Bye-bye.